In this section of sequences and series, we're going to talk about how you can use the nth term to define a sequence. Now, throughout this chapter, you will encounter some finite sequences and some infinite sequences. Now, an example of a finite sequence, for example, is 1, 2, 3, 4, 5, and an infinite sequence is this one here. Now, you'll note that we have the comma and the dot 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 to indicate that the sequence continues. And that's how we see that it is an infinite sequence. Whereas if we don't have a comma at the end and it just stops, it is a finite sequence. That shows that the sequence stops at that term. Now it's worth mentioning another bit of notation. We indicate the first term of a sequence as U1. So we also write the second term as U2, the third term as U3, and hence we can refer to the nth term as Un. And now let's take a look at some examples. So we have here the nth term of a sequence, and it's defined by 3n plus 1. So to find the first term, all we have to do is substitute n equals 1 into our nth term expression. So u1 is equal to 3 times 1 plus 1. So is equal to 4. For the third term, we just substitute n equals 3. Which gives us 10. And for the 19th term, we have to substitute n equals 19. So we'd have 3 times 19 plus 1 is equal to 57, plus 1 is equal to 58. So this nth term is very useful to us because it allows us to jump to any term in the sequence. For this next example, we're told what the nth term is, and we're trying to find out which term has this value. So all we have to do is equate the two. So 149 is equal to n squared plus 5, and we're trying to find the n that solves this equation. So we get n squared is equal to 144, n is equal to plus or minus 12. But can we have a negative 12th term? So at this point it's worth thinking about what n represents, and it is just a natural number. It's just representing which term we're talking about in the sequence, and we don't have a negative 12th term. So at this point we dismiss our negative solution, so we just have that n is equal to 12. Looking over at part B, we use a similar technique. So we have 72 is equal to n squared minus 7n plus 12. We want to subtract 72 from both sides. This leaves us with n squared minus 7n minus 60 is equal to 0. So we want to factorize this, and we can bring it down into n minus 12 n plus 5, so 5 times negative 12 will make negative 60, minus 12 plus 5 will make negative 7, and then we have n times n to get n squared, and we have this. So then our two solutions are n equals 12 or negative 5, but we ignore the negative 5 because it doesn't make sense in this context. So therefore, n equals 12. In this next example, we are told the general form of the nth term of a sequence, but we have it in terms of a and b, and we don't know what those are yet. However, they do tell us what the third term is and what the eighth term is, so we can use that to figure out what the nth term might be. So we have that u5 is equal to 5a plus b, and we have that u8 is equal to 8a plus b. And of course u5 is also equal to 5, and u8 is also equal to 20. So we now have two simultaneous equations. So from the techniques that we learned back in chapter 3, we can use these to solve problems in chapter 6. So if we subtract these two equations, we can get, say, if we call this one 1, we call this equation 2. If we do 2 subtract 1, then we get 8a minus 5a, the b's will cancel, and we get 20 subtract 5. So then 3a is equal to 15, so a equals 5. We can then substitute this into one of our equations, and we can find the value for b. So let's go with equation 1. So 5 times 5 plus b equals 20 equals 5. So then 25 plus b is equal to 5. So then b is equal to negative 20. So we now know our values of a and b, and we're done with this question. So this sort of question is quite common in exam settings. They like to set up different bits of information so that they can set up two simultaneous equations for you to solve. Now, if you're happy with using the nth term, feel free to have a go at exercise 6b.